Regarding the practical application limitations of diodes, several constraints exist, key among which is the maximum power capability of the device. Suppose the current voltage characteristics curve of the diode in the forward conduction region is expressed exponentially. The product of the diode voltage and diode current represents power dissipation, which cannot exceed a physical upper boundary representing the maximum power handling capacity of the diode. Consequently, we expect a boundary curve in both forward and reverse regions where the product of diode voltage and diode current equals the maximum allowable power dissipation. Operating on this boundary represents the absolute maximum power of the diode can sustain. Moving toward the left increases the current while decreasing the voltage, whereas moving toward the right increases the voltage while decreasing the current, maintaining a relatively constant voltage-current product. Based on these characteristics, the actual operating point of the diode must remain strictly within the safe operation region to ensure power dissipation without incurring physical damage to the device. Thus, the permissible operating regions of the diode are defined. Furthermore, the maximum allowable power dissipation is strongly dependent on the ambient operation temperature of the diode. Beyond a specific threshold temperature, denoted as T sub C0, the maximum allowable power begins to degrade rapidly. For instance, if a diode possesses a maximum power rating of 200 milliwatts up to T sub C0 and increasing in temperature up to 100 degrees Celsius may halt the maximum allowable power capacity, reducing it to 100 milliwatts. At a critical maximum junction temperature, denoted as T sub J max, the diode loses all power handling capability. These operation ratings are specified in the manufacturer datasheets. Another fundamental practical limitation is the switching speed of the diode. Transitioning between the on and off state is not instantaneous due to underlying physical mechanisms. Consider a PN junction diode under forward bias, where the p-type region contains majority hole carriers and the n-type region contains majority electron carriers. Under forward bias, when the external electric field overcomes the building potential barrier, majority carriers cross the depleted region. The depletion region wide narrows allow current to increase exponentially. In this state, the duration required for the depletion wide to contract and for carriers to reach the terminals to establish current is defined as conduction time, T sub 1. Conversely, when the bias is reversed, the majority carriers must first return to their respective neutral regions, allowing the depletion Y to expand, after which minority carriers begin to flow. The time required the depletion region transitioning from the majority carrier's response time, we encounter the storage time, denoted as T sub S. This duration represents the time required for current to establish it by minority carriers and for the depletion region Y to widen. During this period, minority carriers move to establish a small current approximately equal to I sub S. Subsequently, there is another time interval known as the transition time or T sub R. Consequently, the switching of a diode between on and off states is not instantaneous. Rather, it is strictly limited by these physical factors. These specific time parameters, which naturally emerge from the underlying physics, are standard specifications provided in manufacturer datasheets across various diode types. Consider a basic circuit consisting of an input voltage source V sub I connected in series with a diode and a load R sub L, establishing a diode current I sub D. Suppose the input voltage as a function of time exhibits a step or pulse profile, transitioning from a high state to a low state. Specifically, at time t sub 1, the input voltage drops from a positive value V sub 1 to a negative value negative V sub 1. Assuming the high state duration was sufficiently long for initial steady-state conditions to be satisfied, the diode initially exhibits a forward voltage drop approximately equal to V sub gamma, resulting in a constant circuit current. However, when the input pulse drops to negative V sub 1 at time t sub 1, the diode must turn off, requiring two distinct time intervals. The first interval, spanning from t sub 1 to t sub 2, is the storage time t sub s, during which majority carriers return to their respective neutral regions. The second interval is the transition time T sub R, during which minority carriers flow to bring the current down to the reverse saturation current I sub S. Consequently, the current does not instantly switch from positive V sub 1 over R sub L, neglecting V gamma, to negative I sub S. Instead, these transient states occur during turn off and turn on switching. Analyzing the turn off transient demonstrates that transitioning from the on state to the off state requires a total time duration equal to sum of T sub S and T sub R. The sum of T sub S and T sub R is defined as the reverse recovery time, denoted as T sub RR. Types of diodes. Among specialized diode types, the Zener diode is a widely utilized component. Zener diodes are engineered to operate mainly in the reverse bias region, where the Zener breakdown mechanism predominates, allowing reverse breakdown to occur at significantly lower voltage than in standard diodes. Consequently, in circuit, polarity orientation of a Zener diode is reversely relative to conventional diodes. When operated under reverse bias, the cathode is treated as the positive terminal and the anode as the negative terminal. Conversely, under forward bias, it behaves similar to a conventional diode. In the region where the forward bias voltage has not reached V sub gamma and the reverse voltage has not reached the breakdown voltage, the diode current remains approximately zero. Thus, the current voltage characteristic curve I sub Z indicates normal condition in forward bias and negligible current I sub S, effectively off, in reverse bias, up to the Zener voltage V sub Z. When the reverse voltage exceeds V sub Z, a significant reverse current flows, exhibiting an exponential profile in the reverse bias region. Zener diodes are manufactured with diverse breakdown voltage rating V sub Z to accommodate various practical applications. Another important device is the light-emitting diode. Among this device class, the light-emitting diode LED emits light outward. Conversely, the photodiode receives light and converts it into an electrical signal. For a photodiode, the current voltage relation indicates that upon receiving light across various illuminance scales, typically measured in lux, the diode current is exhibited in the microampere range. By converting light into electrical signals, it is predominantly used in optical detectors and sensors. The tunnel diode exhibits a unique property where, in a specific region of its current voltage characteristic curve, the slope of current with respect to voltage becomes negative. Consequently, the diode displays negative resistance behavior in the voltage region between V sub P and V sub V, corresponding to current between I sub V and I sub P. Within this region, the ratio of change in current to change in voltage is negative, representing negative conductance and negative resistance. This property makes tunnel diodes particularly useful in oscillator circuits and other specialized applications. The varactor diode utilizes the capacitive behavior formed within the depletion region of a PN junction. Modeling the depletion layer as a parallel plate capacitor, the diode capacitance is expressed as C equals epsilon times A divided by W, where epsilon is the dielectric permittivity of the depletion region, A is the junction cross-sectional area, and W is the depletion region width. By adjusting the depletion region width, the capacitance value can be tuned.